Hello, good evening students. Today I will discuss about some of the reactions of alkenes like ozonolysis and hydration reactions. So first we will discuss about ozonolysis. So as we know, ozone is a reactive allotrope of oxygen which is used in the method of oxidatively cleaving of alkenes and alkynes. So this process actually allows for the carbon-carbon double or triple bond to be replaced by the double bonds with the oxygen. So this is often used to identify the structure of unknown alkenes by breaking them down into smaller or more easily identifiable pieces. So this ozonolysis also occurs naturally and would break down repeated units used in rubber and other polymers. On industrial scale, azelaic acid and pelargonic acids are also produced from ozonolysis. So this is actually the scheme of ozonolysis reaction. So this is a alkene. So when ozone is added, it forms this intermediate which is an highly reactive unstable intermediate called by the name ozonide. So this ozonide, since it is unstable, on decomposition it gives two carbonyl products. And see here, all the steps involved in this reaction are reversible. So let us take up the gaseous ozone is first passed through the desired alkene solution either in methanol or in dichloromethane. And the first intermediate product which is formed is an ozonide molecule which is then further reduced to carbonyl products. So this results in the breaking of carbon-carbon double bond and which is replaced by the formation of carbon-oxygen double bond instead. So the first step of mechanism of ozonolysis involves the initial electrophilic addition of ozone to carbon-carbon double bond, which then forms the mono-ozonide intermediate. Due to the unstable mono-ozonide molecule, it further reacts with and break apart to form a carbonyl compound and carbonyl oxide molecule. So this is a step where we can see the molecule of ozone is added across the double bond of an alkene. So one molecule of oxygen, okay, one oxygen atom from the ozone, it gets bonded with carbon, double bonded carbon atom, and at the same time this results in the breaking of the pi bond between the carbon-carbon atom in an alkene, wherein the electrons of pi bond, they get transferred to the oxygen atom of ozone which is double bonded with another oxygen atom. So as a result, there is a transfer of electron. When electrons are added here, in turn the electrons are added here, and as a result this oxygen gets a negative charge and this gets a positive charge. You know, oxygen is more electronegative. So by this reaction, what we can see, there is a formation of an highly unstable reactive species, intermediate species, which is called by the name mono-ozonide. Okay, and this mono-ozonide further it gives rise to carbonyl compound and carbonyl oxide. So one part of it gives the stable carbonyl compound, other part will give carbonyl oxide. So here In the step 2, the carbonyl and carbonyl oxide, they rearrange the products formed in the first step, carbonyl compound and carbonyl oxide, both gets rearranged and itself and forms to create a stable ozonoid. So ozonoid intermediate. A reductive workup is then performed to convert the ozonoid molecule into desirable carbonyl products. So next type of reaction is hydration of alkenes. Alkenes can be converted to alcohol by the net addition of water across the double bond. There are multiple ways that are commonly used in such transformation. The net addition of water to alkene is known as hydration. So this is the one common example of hydration reaction. This is an alkene. To this water molecule is added. By this addition follows according to the Markovnikov rule. That is, the OH and H. The OH get attached to the double bonded carbon atom which is more substituted, and H gets attached to the double bonded carbon atom which is less substituted. So by this way the alcohols are formed. The result involves the breaking of the pi bond in alkene and OH bond in water and the formation of carbon hydrogen bond and carbon hydroxyl bond. This reaction is typically an exothermic reaction by revolvation of energy of 10 to 15 kilocalorie per mole. But entropy change is minus 35 to minus 40 kilocalorie per mole. Consequently, the net free energy change for the process tend to close to 0 and the equilibrium constant for the direct addition will come to 1. So there are multiple approaches that allow the transformation to be carried out to completion. So if you take up the example, this is an acid catalyzed hydration where the direct addition of water to an alcohol direct addition of water to an alkene is too slow to be of any significance. However, the addition can be catalyzed either by adding by Lewis or Bronsted acids. So this is an acid catalyzed reaction which is shown in the form of scheme. The mechanism involves the electrophilic addition of the proton, that is a acid, to the double bond to form a carbocation. Which is written with a plus charge. The double bonded carbon, when this proton is added here, so it gets transformed into positively charged carbocation. This carbocation intermediate in the second step, the addition of water in the second step result in the formation of oxonium ion. So this oxygen in water is get attracted by the positive charge of the carbocation, that is the carbon atom, and by this way it leads to the formation of oxonium ion, where the oxygen is more electronegative. It donates electron to the carbon, that is carbocation carbon, and forms oxonium ion. So this oxonium ion, it loses one proton, which we call it as deprotonation, and gives the alcohol as the product. So the proton in the oxonium ion, oxonium intermediate, can be deprotonated by any base present, including the conjugate base of acid used as a catalyst, or even by another alkene molecule which can generate another carbocation intermediate and propagate in the chain mechanism. So this is the overall mechanism of addition of water, which we call it as a hydration reaction, hydration of alkene. So this protonation of alkene in the first step of the reaction can occur either at carbon. However, more stable carbocation is preferably formed. The order of stability of alkyl cations or the carbocations is given like this. Tertiary more stable than secondary, in turn is more stable than primary. So the protonation will occur at the less substituted carbon and to create the more substituted carbocation where the water adds. The addition of proton at the less substituted carbon and the OH to the more substituted carbon is known as Markovnikov rule. The carbocation formed in the reaction is prone to the rearrangement if possible. Therefore, the hydration of olefin next to the branched aliphatic center will result in the formation of alcohol forming in a position that was not the part of original double bond. So this is about the regioselectivity of the addition which is followed for this hydration. So this can be shown like this. So this proton, it gets a proton from this, okay, it is get attached here, creating a positive charge that is on the carbon, which is a carbocation. In the next step, this carbocation accepts the electron from the oxygen of water and forms oxonium intermediate. This oxonium intermediate with a positive charge on the oxygen, it loses proton to become stable and gives the alcohol as the product. Thank you one and all.